Alright, welcome to class 4. We're going to continue looking into objects and classes, and I want to go back to looking at constructors, and I'm reusing some of the code from class 2 where we had a rectangle class, and the rectangle had a length and height, and we defined a constructor so we could build a rectangle by saying rectangle double H double L, and we could specify those in the constructor. And so we had a main program that constructed two rectangles. First was a 10 by 12, second was a 5 by 7, and then we could print out their dimensions, and we could change the height of R2 and then print out the new dimensions. And so if I compile rtest.java, and if I run rtest, then it says, R1's 10 by 12, R2 is 5 by 7, and then we change R2's height to 100, and there's the new height and length. I'm doing something different with VI, by the way, just another thing that you can do, right? When I'm editing, if I want to go back and compile my code, I'm just hitting a Control-Z. Control-C does not stop your process, but it puts it in the background, right? So it's stopped, and I can say compile. Compile rtest.java, and I can say run rtest. And then when I want to go back to my VI session, I can just say FG to bring it into the foreground, right? So something we talked about in 224, foreground, background processes. And that saves me from having to constantly go back into VI. And in particular, I've got two files queued up. I got my rectangle class and my main class. So that's just something I'm doing here just to show you a different way to move between tasks. So I can construct this rectangle by putting in these arguments, but if I didn't want to specify arguments, I might just say, I just want a rectangle like this. Well, if I try to compile, it tells me, hey, there is no constructor, right? I have a constructor that wants a pair of doubles, but what it found was trying to use a constructor with no arguments, right? I tried to make a rectangle like this, and it's saying, hey, in the rectangle class, you're required to specify two arguments, right? Height and length in the constructor. So what I can do is I can go into my rectangle class, and I can define another constructor, totally separate from the one above, and I just say public rectangle, but I'm going to say this is a constructor that takes no arguments. So I just say paren paren, and maybe our default construction will just do height equals length equals 1. So if we don't specify dimensions, we just get a 1 by 1 rectangle. And if I do that, I can compile, and when I run it, tells me R2 is a 1 by 1 rectangle. And then when I changed its height, it became a 100 by 1 rectangle. So take a look at this now, right? I've got a constructor, it's named rect, but sometimes I call it with two arguments, sometimes I call it with no arguments. And so this is another thing that differentiates Java from C. In C, the identity of a function is based on its name. If I have a function named blah, anytime I call a function blah, it's calling that function, that set of code. And if I happen to call it, with the wrong number of arguments or something, things happen. But in Java, this function, this constructor that I'm trying to call, is completely different from this constructor. And in the rectangle class, I have two declarations of a constructor. This is one constructor, this is another. They both have the same name, rect, but they're different functions because they have different argument lists. And so in Java, the identity of a constructor or a method in general is a combination of its name and the type of arguments that it takes, and therefore the number of arguments also. So I could make a third constructor, which lets me make a square. So I could say public rectangle I could just say I'm going to take a single double argument, which is length, and height equals length equals len. And so if I construct a rectangle with just a single argument, it will make a square and set both the height and the length to that dimension. So I could say R1 equals new rectangle, let's just call 7. And so now R1 is a 7 by 7 rectangle. So I can have multiple constructors. And how does it know which constructor to use? Well, it's just based on not just the name, but the types of arguments that I pass in. And we can do this for methods too. And this combination of the name and the types of arguments, that's called the signature. And the signature is what differentiates one method from another. So in the practice problems, you'll write a number of methods with the same name but different signatures because they take different arguments. And, you know, in some sense, one of these methods has nothing to do with the other, except that they share the same name, but they're completely independent of each other. They can do totally different things. You know, with constructors, this is probably going to do something similar to this. It's going to initialize a rectangle, but it doesn't have to, right? I could have this kind of constructor do something totally different from this kind of constructor, right? They're completely independent of each other. All right, so that's the notion of signatures. The next thing I want to look at is this idea of information hiding. So when we talk about abstract data types, and think back to when we were developing things like linked lists in 222, we knew that a linked list had a sentinel node. And the way we initialized our list was we called an init function, and it gave us back a pointer to the sentinel. And then we passed that sentinel to all of our functions: insert, search, print, and so on. And that sentinel was just a node, so it has a data field, it has a next field. There was nothing to stop us from doing something like changing the value of the sentinel node's next field, right, to be something other than what it's supposed to be, and breaking our structure in the process. When we implement a stack with an array, we have a thing called a stack pointer. And the stack pointer points to, for example, the next location we're going to push something in this array. But that stack pointer is just an integer. We could look at it, we could change it, we could you know, modify it in ways that would break our stack. So one of the ideas of object-oriented programming is information hiding, and being able to take pieces of our data structure that should not be of concern to the user and actually hide them from the user's view. So for example, when we make a linked list, the linked list, if it needs a sentinel node, we can make that part of the object, part of the linked list object itself, but we can hide it from the user so that the user cannot say, hey, let's change the sentinel node to point to, you know, some random location and break the linked list in that way. So there's some other keywords. We use the word public when we make a constructor. Public means that other code can access this constructor, which is important because if nobody can construct a rectangle except, you know, things in the rectangle class, it's not very useful. By default, these fields in the rectangle class, length and height, they're not exactly public, but they're not private either. There's something called protected. But as we've seen, you know, code in a totally separate class, the rtest class, has access to the length and height. So we may not want that to happen. It may be, for example, that when we construct a rectangle, we do something peculiar to the arguments on the constructor. Maybe we convert them from inches to millimeters. And internally, we always keep our rectangle in millimeters. And we don't want somebody to come in and change, you know, the height to 100 because we really want to scale that by something, right? Or maybe we store the dimensions of the rectangle in an integer for efficiency. And when they pass us a double precision real number, we do some kind of conversion to an integer. So for whatever reason, we may wish to restrict access to these fields, and so we can put a keyword in front, private. And as soon as we do that, anytime that outside code tries to access those elements like r1.height, r1.length, we're going to get an error. And the error is height has private access inside this class. Alright, well that's nice for hiding information from the user, but you know what? Sometimes the user may actually want to get the height and the length of the rectangle. So how are we going to give the user access to these fields? Well, we can do the following. We can make what's called a accessor or a getter that will allow the user to read the height and the length of this rectangle. So let's make a pair of accessors. So the accessor is going to be a method, and it's going to be public, and it's going to return a double. And the traditional name for this is get followed by the name of the thing you're going to get, but camel cased, so starting with an uppercase letter. And it doesn't need any arguments, and all it has to do is return length. And then over here, instead of saying r1.length, I'm going to call this method r1.getLength and concatenate that to my string. Alright, why is this going to work when the previous thing did not work? Because this getLength method is public. So I'm allowed to call this method, and inside this method, right, this code has access to length because it's inside the class where length is declared, right? It's private, but inside this body of code, we have access to it. It's private to things outside of the rectangle class. But this accessor is absolutely able to read that variable and then return it, and since this is a public method, it will give us access to it. So we can make a getHeight method that also returns the height. So now I can change this to getLength. And I can change this to getHeight. And I'll change this to getLength. Alright, so now if I try to compile, I've only got one line it's going to be unhappy about, which is where I try to change R2's height, because again, height is private. So let me just comment out this for the time being. Compile that, that'll compile fine. Go ahead and run it. And it says R1 is a 7 by 7, R2 is 1 by 1, and R2's new height is 1 and its length is 1. So I can read these private fields by using these accessors, but if I try to change the height of these, it will give me an error saying, hey, you don't have access to this, this is private. Now, it may be that I want to allow the user to change the dimensions of a rectangle, and so I can make a counterpart to an accessor. I can make what's called a mutator. And the way a mutator looks is we say public, and instead of get, we call it set. So it doesn't return anything, it's void. We can say set height, and we give it an argument. And we'll make this public, so I can say set height, give it an argument, and then again, this code has access to the height field, so we'll set the height field equal to h. And then I can do the same thing for length. I'll call it L just to make it a little less confusing. And I can say length equals L. So now I can compile this. And I still can't access the height field like this, but now I can say r2.setHeight 100. So that'll compile fine, and when I run it, I was able to change R2's height from 1 to 100. So these are accessors for getting access to a field, and this is a mutator for changing a field. Now, why would I want to do this? Why would I want to make these things private? Well, for example, you know, as is, I can set the height of my rectangle to be negative. And if I do that, you know, I've got a minus 100 by 1 rectangle, and if I compute its area, it's going to be a negative number. And if I try to square that, I'm going to try to take the square root of negative 100, and I'm going to get all kinds of strange things happening. And maybe I never want a rectangle to have a negative height. So I could do something like this inside my mutator. I could say if L is less than 1, I'm just going to return. I'm not going to change the length. And similarly, if I try to set my height to be less than 1, I'm just going to return and not change the height. So now, when I try to run my program, I made a call to set height of negative 100, but it ignored that, and it left the height at just 1. Now, you know, in practice, I would probably want to do something to let the user know that they used an illegal argument and that I ignored it. But as an example, right, this is a way that we can control people's access to these private fields. We can let people read these, we can let them control them, but let them modify them, but only within certain bounds, right? So it lets us put constraints on what code outside of this class can do with pieces of this data structure. So that's scoping of variables, that's access control, and we'll do this a lot with particularly, you know, for writing accessors and mutators, or getters and setters as they're called sometimes. So that's something that leads towards, you know, information hiding and helps us with this idea of building up objects. All right, so next thing I want to do is look at the LinkedList class, and this is a large class that implements linked lists just like we built them by hand in 222, but in Java they're a readily available type of data structure, and so we can simply use these linked lists and build on top of them. So let's take a look at linked lists. All right, so let's take a look at the linked list class in Java, and this is a, you know, pre-existing class that's available for us to use. So first of all, we have to import it from Java utility linked list, so much like a scanner. It's got this extra thing over here, an angle bracket E. We'll talk about that in a few minutes. We can construct a scanner by just saying, you know, linked list paren. We don't need to give it any arguments. That's like our initialization of a linked list. But then take a look at all the methods that are available, right? So we can delete all the elements from the linked list by saying clear. We can add to the end of the list. We can also add somewhere in the middle by specifying a position where we want to add an element. We can add to the beginning of the list with add first. We can also remove from the first element of the list, right? Remove the head. Well, what does head mean, right? We're talking about queues. We can treat a linked list like a queue. Well, we know how to do that. We did that in 222. This linked list class supports treating the linked list like a queue. There's also a function called push and a function called pop. We can treat this linked list like a stack, right? This is all built into this one class called linked list. and we can do all of these different things with it that we had to do kind of by hand, piece by piece, building it up in code in 222. So this is a very powerful class. We can convert our linked list to an array, right? And just make an array of whatever is in the list and then treat it, you know, the way we treat arrays. We can find out the number of elements in the list by calling a size method. We can remove the last element from the list. We can remove the first occurrence of a particular value or, you know, type of object in the list, and so on and so forth. So all of this is available to us. The business with the angle bracket here has to do with the fact that a linked list is what we call a generic class. So think about a linked list. When you write code for linked lists in 222, we have a data field and a next field in our node. And the data field, if it's a list of integers, it's an int data. But if it's a list of strings, it's a char star data. If it's a list of doubles, it's a double data. If we had that field pointing to, you know, a tree, for example, it would be a struct node star data. But whatever we make that data field point to, it doesn't change the logic in the rest of the list, right? The way that we move down the list, the way we traverse it and print it out or search for something or remove a node is independent of what type of data is stored in the list. So with this linked list class that's available in Java, this one class will work with different types of objects, integers, strings, and so on and so forth. But we do have to tell it what kind of thing we're planning to store in the list so that it can, you know, set up the nodes of the list in an appropriate way. So let's play with this linked list class. So I'm still sitting in my class 4 area, and I've got a few scripts that I'm going to make free use of to help me write Java code a little more efficiently. So one is a script called init, and I'll just make a class called LLTest. So I can vi LLTest, and it just kind of creates this boilerplate for me with a description of the class and then an empty main method. So that's just a little bit of time savings. I'm going to do an import, and I copied that name of the import area from this page when I had it highlighted. I just did a Control-C to copy it. So there's my import, and let's make some linked lists. Let's make a list of integers. So as usual, we put in the name of the class, linked list, list1 equals new linked list. And then let's add some data. So I'm going to say list1.add. And we'll just start adding some numbers in here. So let's add a 23 and an 18 and a 22 and an 11 and a negative 15. All right, so we're adding some stuff into the list. And easiest thing to do with a list is look at it. So we're just going to print it out. We'll say system.out.println list1 equals, and we'll append list1 to that string. All right, really simple code here. So I can compile this, and I'll just say C for compile, but I'm going to get some warnings, right? It's going to tell me that I use unchecked or unsafe operations, and it says recompile with -excellent. So I'll recompile that. Well, let me do this with a Java C -excellent LLTest.java. And it will give me a bunch of warnings, right? And the first warning says raw types found. Linked list, list1 equals new linked list. Missing type arguments for generic class linked list, angle bracket E. So this angle bracket E is like a parameter, and it's something that needs to be specified to say what type of elements are we going to have in this list. Now this will run and it will do something close to correct as is, but if you're getting 7 warnings in your program, consider that a problem. If you're getting 1 warning, consider that a problem. So let's make this thing generic. So we have to do 2 things. We have to put, after the declaration of the variable, the type of thing that's going to be in the list inside angle brackets. And then when we call the constructor, we have to put the angle brackets there also. And then after that, this is just a linked list of integers. And we can call all the methods as usual. We can add, we can remove, we can search, we can put things at an index, and we can also concatenate it to a string. All right, so if we do that, I can compile it. And if I run it, then when I turn this list into a string, it's a set of numbers inside square brackets separated by commas showing me the values that were added. Right, so I added 23, 18, 22, 11, minus 15. Well, there's the values I added. So I've got a list all of a sudden, right? And it takes very little work, right? This is the only line that has a bit of weirdness to it with this parameter, angle bracket integer. But you know, this is declaring a list 1 as a linked list of integers, and then this is constructing a linked list of integers. And now I can go ahead and I can add things to that list, and I could say something like right, I could use the size method to find out how many elements are in the list. Or I could do other things, right? I could peek at the first element in the list but not remove it, and so on and so forth. So if I do this and I compile and run this, it should tell me my list has 5 things. Let's go ahead and add a few more things to our list. Let's put a few more 11s in there. We'll compile that. And then we'll run it, and it tells me the size of list 1 is 8. Well, 1, 2, 3, 4, 5, 6, 7, 8 things in the list. So there's a list. We can do what we want with it. And we didn't have to write any code, right? We're just using this as basically a built-in type of thing that's available to us. Now, suppose we want a linked list of strings. Well, I can change this to string. And so I can add some strings like hello, fun, cool. Right, so now I'm building a linked list of strings, and I'm still using the same add method. I'm just calling the add method with an argument that is a string instead of an integer. And I can still concatenate that list to a string and turn it into a string. I can still call the size method and see how many things are in my list, and so on. So I can compile that, I can run it, and there's my list. Hello, fun, cool, exclamations, penguin, and haha. Size of list 1 is 6. So all these things are available to us. And, you know, we've got linked lists. In the problem set for today, you'll play around with some of this stuff, but you'll also use it to make a linked list of rectangles. And that works beautifully well if you use the rectangle class that we developed a little while ago. we can do exactly the same thing, but instead of saying integer or string, we can just say rectangle, rectangle, and then we can add, instead of a string here, we can add our rectangles, R1, R2, and get a linked list of rectangles. So this is how we can start layering data structures. We can make a linked list whose elements are trees, whose nodes are, you know, some other kind of structure. And that's a really powerful way to work with data structures. All right, and if you're curious, this compile command I have is just running a short bash script called jcomp that basically lets me type in, you know, I can say C followed by either, you know, filename.java or just filename dot or just the file name, and it will strip off that trailing dot and Java, put a Java on the end, and then call the Java C command. So I can say compile ll test like that, or I can compile lltest.java, or if I'm using, you know, tab completion, it will take me out through a dot because I've already got a .java and a .class. I can do it like this also, and it will still compile lltest.java. And then the run command is just a JRun. It does the same thing, but it strips off the .class. So I can say run lltest, and the class won't come up. So those are just shortcuts, right? And the init function, if I just say init, it makes an empty main.java. If I say init ha ha ha, it makes a ha ha ha.java. So just some shortcuts, you know, to keep making things a little easier, a little more efficient. I don't want to have to type this in over and over and over again. And, you know, in some sense, this is moving towards having an IDE, because IDEs will create this boilerplate code for you. But this is not as extreme as an IDE. We're still working at the command line. We're still editing. We're still figuring out the syntax for ourselves. So this is kind of a happy medium between having to do all the mechanical typing of the same thing over and over again versus, you know, having some system that just basically writes the code for us. So that's just some tools I'm using just to make development a little more efficient here. All right, so so that's basically it for this. Take a look at the problem set, bring questions to class. We'll work through the problems in the next class. I'll see you next time.